Before I start, do you have any questions? So I will continue the discussion on the error estimation in Monte Carlo simulation. In Monte Carlo simulation, in general, okay, in this case, for example, the Ising model, okay, the expectation value of any observable can be measured by averaging over the configurations. Okay, so this is the expression. Okay, and so this is here. So it's the average over the configurations, and this is the expectation. Okay, so each configuration is weighted by this probability. Okay, and the probability is proportional to minus of the energy of the configuration divided by KT. Okay, so no matter what's the observable, okay, it's always multiplied by this probability, okay, of this configuration, and then sum over all possible configurations, and then you get the expectation value. Okay, the T is the summation over the probabilities. Okay, then that's called partition function. Okay, and in the Monte Carlo simulation, we can replace this exact summation by this approximation, say by sampling the configurations with this probability distribution. Okay, so each CK sampled here, presumably, getting this configuration is proportional to this probability. So, so this factor can be omitted in this summation. So we can just sum over this configuration CK and then get the average. Okay, so this probability has been embedded in the process of the sampling. So depends on how much computing resources you have. If more computing resources, then you can sample more configurations, and then you get the error. Okay, error of the estimate. So this is the mean value of the O observable. Okay, and there is the error of the mean. Okay, so E of the O expectation value is error of the mean of the O. Okay. If the distribution of the mean value obeys the Gaussian distribution in the limit n go to infinity, okay, then this according to the central limit theorem. Okay, then the variance will be the error of the mean. Okay, the variance, okay, of the mean, okay, is proportional to the variance of the observable divided by n. N is the number of measurements. Okay, number of configurations you sampled. So so if if each configuration is statistically independent, then the error of the mean is proportional to that. Okay, so here is the presumably if there's no correlation between the configurations, then we can use the central limit theorem. Okay, and then estimate the error of the mean. Okay, just by computing this. Okay, so this is the variance of the observable divided by n. Okay, and the square root of the variance is the error of the mean. Okay, but in Monte Carlo simulation, let me go to a full screen. Okay, so you can see it more clearly. Okay. No. I should go to the, let's see. Here, this is the full screen. Okay. But in the Monte Carlo simulation, the configurations, okay, generated are not statistically independent because the later configuration are generated, okay, then the sequence, okay, is from the generated in the sequence. And each configuration depends on the previous configuration, okay? So, of course, you can sample two configurations separated by many swaps, okay? Then it's more likely to be statistically independent, okay? But still, okay, there may still be some dependence, okay? So in that case, the error of the mean should be corrected as well, okay? So, so if in the ideal case, okay, all this correlation, okay, yeah, this autocorrelation function is zero, okay, so M, Cm. So the is defined as the observable at the ith configuration, okay, and then this is the I plus one, I plus m configuration, okay, and this border, and the expectation value, okay. So that means they are these two configurations separated by m, yeah, sampling, okay, yeah, and then minus of the OI expectation value, and then maybe, yeah, it can also be written as the OI and the OM, okay, yeah. So you always say this I and I plus M, and then 1 over all the entire sequence, okay. And this configuration always separated by M, yeah, samplings, okay, yeah. So this is the autocorrelation function. Yeah, if the configurations, okay, at M, okay, separations, really statistically independent, then this C, okay, will be almost zero, okay, very small number, okay, yeah. In practice, okay, this is not zero, okay, yeah. Only when M is getting very large, then it becomes smaller and smaller, okay. So this, the C1, C2, and so on, okay, at some point, okay, it becomes so small, okay, and then you can get the further dependence, okay, all the CM, yeah, higher CM, okay, yeah, CM plus one and so on, okay, if this, so then you can sum all this, okay, uh, uh, all this autocorrelation function contribution, okay, add together, and then this one plus something, okay, so then you get this is the correct, okay, error estimate, okay, yeah. So yeah, it's the fixed interval in the simulation sequence, okay. No matter how you define the interval, okay, this interval can be, say, in the Ising model, okay, it can be separated by, say, 10 swaps or 100 swaps, that up to your choice, okay. So the appropriate sampling interval can be estimated from the value of m for which Cm becomes small, okay. So yeah, you can estimate the Cm, yeah, when you say at which m, okay, it becomes sufficiently small. And then you can sample the configurations, always sample the configuration separated by this interval. And then you at that point, then you can see, okay, these correlations are almost vanishing. That means the configuration are statistically independent. And then the error of the mean would be just the sigma of O divided by square n. Okay. Yeah, but in practice, okay, yeah, we do the simulation, and then we don't know what's the m, okay, in such that Cm is very small, okay. So in that case, okay, then we have to estimate, okay, yeah, what are these numbers in this sequence, okay, what are the correlations, okay, yeah, such that, okay, I can get a correct estimate of the error of the mean. Okay, yeah, how do I get this formula? Okay, so actually that's just a simple mathematical derivation here. Okay, so yeah, as I said, okay, this is the derivation in the next page here. Okay, so this is the detailed derivation. Okay, so it's a very simple algebra. Okay, yeah, you can go through it. Okay, and if you have any question of the derivation, okay, let me know. Okay, then I can explain to you. Okay, but yeah, here I don't walk through the derivation in the class. Okay, so you at this point, okay, you just take it for granted. Okay, so so this is the error delta A square. Okay, so delta A square is the, yeah, since I have n measurements, have AI. Okay, and then this A expectation value here, okay, is the true expectation value, not the average of the AI. Okay, so it won't otherwise. Okay, if this mean, okay, is the mean of this n measurement, then it must be zero. Okay, no, here this is the true mean value. Okay, yeah, not the not the mean value of this n measurements. Okay. So yeah, so after some algebra, okay, then can obtain it to be AI minus a true expectation value. Okay, true mean value. Okay, this is the square. Okay, and yeah, so this is the variance. Okay, of the A. Okay, and yeah, divided by this n square. Okay, so that is the variance of the mean square. Okay. And then besides that, okay, there's other terms. Okay, so this is the sum over I from 1 to n, and then sum over j from I plus 1 to n. Okay, yeah. So this is AI aj. Okay, so sum over all the correlation, okay, of this sequence. Okay. So the derivation is here. Okay, so you can yeah, go through this derivation. Okay, it's quite straightforward to follow. So written in the each term explicitly. Okay, written out each term explicitly. Okay, then this is the, say, I plus 1. Okay, so they are correlation of one step. Okay, yeah. So all correlate all measurements separated by one step. Okay, and then all measurements separated by two steps. Okay, and so on. Okay. Yeah, and the last term is this. Okay, so yeah, so this is the largest separation you can have. Okay, in this n sets of measurement is this, and yeah. But as I said, okay, yeah, this term, okay, would getting smaller and smaller as the separation getting larger and larger. Okay, yeah, and the interval getting larger and larger between these two measurements. Okay, and then the term would become very small up to some point, and then you don't have to add all these terms. Okay, only add this up to the point. Okay, say it is less than some small number, epsilon, say 10 to minus 10. Okay, and then this summation terminates at that point. Okay. So the true error, okay, or the true variance of the mean, okay, is the variance of the observable or the variable, okay, divided by n, okay, and then usually, okay, this n is replaced by n minus 1, because if you just make one measurement, okay, then you cannot estimate the error at all. Okay, so in that case, okay, the error is infinite. Okay, yeah, because you make one measurement, you don't know what's the error. Okay, so this reason why I have this conventionally. Okay, this is replaced by n-1 rather than n. Okay, but if n is big enough, okay, it doesn't matter n or n-1. Okay, so this is the if all the configurations are statistically independent, then this is the error of the mean. Okay. However, the configuration are not statistically independent, so the measurements AI are not statistically independent. Okay. Then you have to add this correction. Okay. The error estimate due to the correlation. Okay. So this is the autocorrelation. Okay. So this CJ, okay, can be written in this form, or more generally, okay, it can be written in this form. Okay. In general, okay, this is the more formal expression. Okay. AI plus J. Okay. In general, AI is not equal. The expectation rate not equal to AI plus J. Okay. Imagine that. Okay. You have AI and then AI plus J. Okay. So say, for example, AI and AI plus 1, okay? So they are two different measurements, okay? And then if you moved it in the sequence, okay? And these two are, so always this, okay? So not necessarily, okay? AI and AI plus J is the same, okay? Yeah, especially when the J becomes large, and then the numbers, so some of the measurements, okay, can only be reached by J, but not by AI, okay. So in that case, okay, it's better to estimate the mean, okay, individually for I and I plus J, okay, yeah. And then the downstairs is the AI squared minus AI expectation value, and then minus AI, and then expectation values, and then take the square. Okay. Yeah. So yeah, I have a sample. Okay, sample code using this as a CJ. Okay, and then to estimate the error. Okay. Yeah. So including this, and then as I said, okay, the summation here. Okay. Yeah. At most, you have the summation up to J from 1 to n minus 1. Okay, because you only have n measurements. Okay. Yeah. So yeah, but this summation terminates at the point when Cj getting very small. Okay, and then that summation no longer go to higher J. Okay. So so let me show you the code and see how it works. Okay. So this is the auto T B plus C. Okay. Yeah, compute the integrated autocorrelation time. The integrated autocorrelation time means the one that is the yeah, I will define later, but actually there's a sum over all the CJ. Okay, and then at the constant term is the 1. Okay, come from the 1. Okay, so yeah, and then I have a input file. Okay, yeah. This is input file is the result of the simulation. Okay, using model actually. Okay, and that is the energy and the magnetization. Okay, yeah, measurement, and then pin out to a file. Okay, and I can always choose the number of measurements. What's the n? Okay, and then the Tmax for computing integrated autocorrelation time. So this Tmax can be chosen. Okay, yeah. Yeah, of course, Tmax cannot be bigger than the number of measurements. Okay, yeah.
Sorry,
Yes.
are you in terminal?
Oh, sorry. Yeah, I did not switch to the terminal. Okay. Yeah. Okay. Okay. Now you see it. Yeah. Okay. Yeah. One of the yeah we yeah. So okay. Now you see the code. Okay. Yeah. Um. So there's a data file. Okay. And that is from the Monte Carlo simulation, okay? And then there are two columns, okay? One column is the energy, the other column is the relaxation, okay? And then I have about, say, 10,000 of measurements, okay? Yeah. So, and then I can choose any number, okay, to test, okay? This uh, this is the auto correction error or integrate auto correction time, okay? Yeah. So this is the array for the observable, okay? Yeah. And I can yes, from the file, I can just read in the data, okay? So depends on which observable I choose, okay? So I have to select from the column 1 or column 2 or column 3, okay? Yeah, up to my choice, okay? So so I have two different, you can see, okay, AI here, this is the second column, and this is the format, okay, is, well, when this is the only have the two column data, okay, so yeah. So here, just get the average, okay, and then the A square average, okay. So this is the computation uh, of the error of the mean, okay. Yeah, if all configuration are statistically independent, then that's the answer, okay? But since the configuration are correlated, so I have to compute the CJ, okay? Yeah, so to compute the CJ here, I have to get the AI average, okay, and the AJ average, okay? And also the, AI and AJ, okay? So, and then the J is the separated from I by separated by T, okay? And then here I have to sum over all possible separation, okay? That is the T, okay? Sum over T from 0 to T max plus 1, okay? So here, this is the A correlation, okay? So that is the CT, okay, or CM, the upstairs of the numerator of that, okay? Okay, and then divided by yeah. So this A correlation TJ T, okay, and there's the upstairs of the CJ, and then the downstairs, okay, just the A correlation 0, okay, and there's the no separation, okay, yeah. So there's the 0, okay, yeah. T is 0, okay. So yeah. So the CJ, okay, is the ratio of these two, okay. So now if the C, okay, is the less than the epsilon, okay, epsilon in this case I say to 10 to minus 12, okay, so very small number. So after when the C, okay, getting so small, okay, less than the 10, 10 to minus 12, and then I just stop the summation here, okay? So I don't have to sum over for any CJ, because CT, okay, bigger than that, okay? So that this is the tau T, okay? So each time I add this all together, okay? So there is the sum of the CT, okay? So this is the so I can pin out, okay, the summation, okay, is up to which point, okay, up to block T, and also the tau T, okay, the integrated autocorrelation time. T is here, the summation of the at the point, okay, when CT, okay, becomes smaller than the epsilon, okay. Yeah. So, and then this is the tau, integrated tau, is sum over all the CT, okay. Yeah. Or here is sum over all the C, okay. C, actually, this is the CJ, okay. Yeah. Yeah. Okay. So this is the result, okay. Yeah. And then the error, okay, is this, okay. Then this is the error of the Monte Carlo simulation, okay, is the this, okay, 2 times tau in, okay. So this is tau, 2 times tau in here, okay. Yeah. And then so this is the average, okay. Here is the average. Average is here, okay. So here, okay. So this is the average, okay. And then the error, okay, is the estimate by the square root 2 tau in, okay. Okay. Yeah. Times the, okay. This error, okay, here is this. Error Monte Carlo. This is the naive error, okay. This is the error of the, when all the configurations are statistically independent, okay. And then multiply this factor, okay, is the ERRMC, okay, is the after the take into account of the correlation, okay. Yeah. So yeah, and yeah, if you get the integrated autocorrelation time, yeah, you get the correlation error, okay. Then there's the naive estimate, okay, and that's why I said this is incorrect estimate, assuming statistically independent data. Then only this term, okay, without the factor ERRMC, okay, okay, error due to the Monte Carlo, correlated Monte Carlo, okay. So, yeah, okay. So let me show you the input data file, okay. Okay, here. So there are 3 columns, okay. This column is the energy measurement. And this is the monetization, I believe, okay. And there's other data, okay, here, okay, yeah. So, so I in this case, in the code, okay, in the code, I choose the first column, okay, as the observable, okay, and then to estimate is the error of the mean, okay. So, okay, so the input auto T, okay. So suppose I just take the 4096 and then 1024, okay, yeah. So the 1024 is the Tmax, okay, yeah. So, yeah, auto P, P, okay. So you see, okay, yeah, Tmax is the, yeah, I just take the total number of the measurements, 4096, okay. And then the Tmax is the 24. Okay. Yeah. Then I got at the T, when the separation is 103. Okay. Then the CT already is less than the epsilon, 10 to minus 12. Okay. So at that point, I just terminate the summation. Okay. And then I get the tau integrated. Okay, is 8.45. So square root of the 2 times. So it's a factor of 4. Okay. So there's a factor of 4 due to the autocorrelation. Okay. So the correct error, okay, yeah, is this. Okay, this is the only the assuming the this. So this is the by the statistically independent configuration. Okay, then the error is just the error of the variance or of the observable. Okay, divided by n squared n. Okay, but then you have to multiply this factor in order to get the correct estimate. Okay. So this squared 2 times integrate tau in. Okay, is the after you multiply this factor, then you get the correct error estimate. Okay. Yeah. So let me return to the slide. Okay. Then the term integrate autocorrelation term will be more transparent. Okay. Yeah.
I'm sorry, Professor.
Yes.
I'm
You
trying
have a
to
question?
yes, I have a question.
Yes.
So I'm trying to condor submit, but it says that failed to connect to local queue manager, and I tried JView, the command line JView, and it says failed to connect. Is it my problem here?
The GPU cluster has some issues now, has some problem now. Okay, I'm going to fix it. Okay.
Okay.
It only happened in this morning, and it's unclear what had caused this problem. Okay. Yeah.
Okay.
So I don't have the time to fix it at this moment. Okay. But
Thank you.
I hope it can be fixed later today. Okay.
Okay. Thank you.
So let me return to the slide. Okay, here. Okay. Yeah. So what I have done in the auto TB, okay, is the sum of all this, okay, sum over all this of this CJ, okay, up to the point when CJ is less than epsilon, okay. So yeah, and this term was computed in the beginning. Say, yeah, assume there's the A error, okay, the error, okay, yeah, that is for the statistically independent and configurations, okay, so there is the So the tau integrator is just 1/2 plus tau A over tau. Okay. So tau A over tau is nothing but just the sum of the from when J equal 1 to Cj. Okay. You see? Yeah. So this is the what I call the integrated autocorrelation tau. Okay. So CT here, this term, okay, is called the correlation, okay? Yeah, and then integrate over, okay? So it's an integrated autocorrelation term, okay? Yeah, so this is summation of the Cj and J from 1 to the value until, okay, Cj is 0, okay, or Cj less than certain small number, epsilon, 10 to the minus 12, okay? So there's the tau in, okay? Yeah. So the error of the mean, okay, yeah, is this square. So this is the mean value, okay, yeah, and then square of the delta A square. So this is the square of the variance, okay, and the square root of variance, okay, is the this, okay, yeah, variance, okay, this, and then square root of this expression here. So that's the square root 2 tau in, okay, okay, so you have the 2, so this is the square root of 2 tau in, okay, so delta A, take the square root of that, you'll get this square root of this, and then square root 2 tau, okay. So this is the error for the when there's no correlation between the configurations, no correlation between the measurements. Okay, and this factor here taking into account of the correlation. Okay, so it come from here. Okay, so you see if all CT is 0, okay, then this term is 0. Okay, and then you get a 1 here. But since the correlation is not 0, okay, then you have to take into account of this, okay, and then this corrected, okay. So the error turns out is larger, okay, and this larger up by this amount, okay. So yeah, and as you see, okay, yeah, this factor, okay, can be turn out to be much bigger than 1. Okay, so in the example I show you, okay, this square of this square 2 tau turns out to be 4. Okay, so that means, yeah, 4. So this is the 1 plus, say, 15. So there's 16, and let's take the square root. Okay, it's 4. Okay, 4 something. Okay, so this yeah, you can see this number could be quite large, much larger than this one. Yeah. Okay. Yeah. I go back to the example. The example code. Sample code. Okay, and then you can see it more clearly. Okay. Okay. Yeah. So you can see, okay, square root of 2 tau in is 4. Okay. So you can see 2 tau in is say 16 something. Okay. 16 something is 1 plus something. Okay, 1 plus that. So that means the 2 times sum over of the CT. Okay. Yeah, up to t equal 103. Okay. Yeah. Then that is the, yeah, that means the 2 times sum over CT up to t equal to 103, okay, that is around, say, 15 something, 15.11 something, okay? Yeah, 15 point, not even 11, because when you take a square it, okay, so 15 something, 15, yeah, okay. Okay, after you square it, then you get 16 something, okay, minus 1, okay, and that's the thing due to the 2 times sum of all the CT, okay, up to CT less than 10 to minus 12, okay, so negligible. Okay. Okay, so all the Monte Carlo simulation, okay, especially this Metropolis algorithm, okay, yeah, you always have to estimate the error, okay, in this way, okay, take into account the autocorrelation of the configurations, yeah, because in the simulation, the configuration are correlated, okay, yeah, okay, yeah, you don't know, okay, yeah, at what point, okay, yeah, it becomes not so correlated, okay, becomes independent, okay. So you cannot no, you don't know, okay, in the beginning, okay, yeah, how many simulation you have done and how your measurements should be, what is the interval, okay. We know when the interval is getting larger and larger, then you will get less and less correlated configurations, okay. But it's impractical, okay, you separate it with too large, okay, and then the number measurement n will become small, okay. So in that case, okay, you get a large error, okay, due to n is very small, okay. Remember the error, okay, is proportional to square 1 over square n, okay. So you always try to increase the number of measurements, okay, on one hand, and on the other hand, okay, the the configuration, okay, the measurements are as near as statistically independent as possible, okay. But you cannot have both, okay, yeah, to the optimal case, okay, because yeah, you increase the separation, then the number of the measurement you get will be small, okay. So if you have the more measurement, okay, that means n is larger, and then the separation between the measurement will be small, okay. In that case, they are more correlated, okay. So so in running a simulation, after you run the simulation, and then let's say the measurement are separated by such an interval, okay, and then how many measurements, okay, that means how many swaps in the case of the two-dimensional Ising model, okay. Then after that, then you get the results, okay, and then you can obtain the mean value and also the error of the mean, okay, and then you have to estimate the error of mean using this method, okay, using this measure the autocorrelation, okay. Oh, yeah, integrate autocorrelation time, okay, to get the correct estimate of the error of the mean, okay. So you can see, let me switch back to the transparency, okay. Okay. Yeah. So in order to measure the C, okay, the integrated autocorrelation time, okay, you have to sum over all this CT, and then you have to the measurement has to be very large. Otherwise, it's hard to measure this. Okay, yeah. So in some of the simulations, in some physical systems, okay, yeah, if you can do, say, 100 measurements or a few hundred measurements, okay, it's already the most you can get within your computing resources, okay, with your computing resources. So in that case, okay, yeah, it's hard to measure the integrated autocorrelation time, okay. For the Ising model, it's no problem. For the Ising model, you can always say, yeah, have the 10,000 measurements and then, yeah, so on, okay, yeah. And then in that case, you can measure the integrated autocorrelation time easily, okay. Yeah, but for some other situation, for example, the QCD, okay, I've been working on, okay. And yeah, at most, I can only generate, say, yeah, a few hundred configurations and then do a few hundred measurements, okay. In that case, okay, I cannot measure. I can use, it's almost impossible to use this method to get a correct estimate of the error. So due to the correlation of the configurations, okay. So in this case, okay, I have to use another method to do the error estimate, okay. So this is called the binning method, okay. Yeah. As I said, okay, in practice, CT is notoriously difficult to measure, okay. A way to obtain the proper error estimate for Monte Carlos is by blocking the data, okay. So this is the binning the data, okay. So I average NP successive measurements, okay. So that means I block the data, okay, to each block, okay. Each block have a NP measurements, okay. Yeah, say suppose I have 100 measurements, okay, and then I block it, say, to 10 measurements, okay. Then I have 10 blocks. Each block has the 10 measurements, okay. And then I form an average of each block every 10 measurement. Then I form the block average, okay. Yeah, yeah. If the block is large enough, okay, say the number of blocks is large enough, say, then the autocorrelation successive block will be small, okay. Yeah, because you can see, okay, yeah, if even though there's an individual measurement, maybe have a correlated, but then when you take the block average, then the block average is the average over many configurations, okay, successive NP successive configurations. So the correlation between the block average, okay, yeah, will be small if the blocks are very large, okay, sufficient large, okay. So if for the NP is sufficiently large, then the C tau will be behave, C tau, okay. C tau is the autocorrelation, okay, between blocks, okay, between the blocks. So C tau is so this is the separation of the block, okay, yeah, by this separation tau, okay, yeah. And this C tau, okay, is roughly proportional to 1 over NP. So that means if NP is large enough, so the number of successive measurements to form the block is large enough, okay, then this will be small, very small, okay. So yeah, so I can estimate the C tau, okay, yeah, by increase the NP, okay, until the C tau is very small, yeah. But in this case, provided the number of blocks, okay, is sufficiently large throughout this process, okay. So you can see, okay, yeah. So for fixed number of measurement, this is almost impossible, okay. Yeah, because when you increase the number of n measurement in a block, then the number of blocks will become small, okay. Yeah, you have 100, okay, 100 measurements. So if you have 10 measurements per block, then you have 10 blocks, okay. you have a 220 measurements per block. You only have 5 blocks. Okay. So this is you cannot have both. Okay. Yeah. If you have a large number of measurements per block, then the number of blocks will be small. Okay. But anyway, I can measure the variance of the block average. Okay. And just measure it. Okay. For several value of B. Okay. For changing the value of B. And then in this case, and then extrapolate to get the error estimate. Okay. So I change the value of B and B. I change number elements in the block, and then extrapolate this. Okay, this delta A. Okay, this variance. Okay, this variance depends on the NB. Okay, yeah, and then until the increase the NB until the delta A saturates. Okay, that means when you increase the NB, at some NB, okay, then the delta A will be more or less the same. Okay, saturate per 2. Okay, then the saturate per 2. Okay, can be taken as the error of the mean. Okay, yeah, if you increase the NB further, okay, then it will become small. Okay, because the number of blocks becomes small. Okay, in that case, NB is very large, and then the number of blocks is small, and then the delta A will decrease again, or it will increase more. It behaves can behave unpredictably. Okay, so but in some values of NB, you can see delta A saturates, and then there's the per 2, and then I can take this per 2 to estimate this as estimate the error, okay, of the A, okay, yeah, and that includes the correlation, okay, yeah, so you can see, okay, so and when NB is 1, then this is just the assuming, okay, all are statistically independent, okay, so that it must be small, okay, when NB is 1, okay, then the delta A here, okay, is similar. You assume that all the configurations statistically independent, and this is the error, and that this error is small, okay, but when you increase the NB, okay, then you can see delta A will increase, okay, and then at some point, at some value of NB, and then delta A will saturate, okay, more or less not changing, okay, like per 2, and then you can take this value as the estimate of the error of the A, of the error of the mean of A, okay, so so the saturated delta A is taken as the error of the mean, okay. So I show you how this method works, okay. Let me switch to the terminal, okay. So this is the binding, okay. So yeah, this code is in Fortran, okay. So you can compile it with the G Fortran, for example, okay. And in Fortran, I can also have a allocatable array, okay. So it's just similar to the C, okay. I allocate a pointer, okay. So this I don't have to fix the size the array, okay. Yeah. So this is the bin size, okay. I just in the beginning I said the enter how many bin sizes, okay. Yeah, how many different bin sizes, and then for each bin size, then I know how many blocks, okay. Yeah, and then so this this the block, compute the block average, okay, yeah, and then compute the variance of block, okay, and then the pin out the data, okay, that's it, okay, so very simple, okay, yeah, you can write your C code, okay, yeah, and then I use the same data file, okay, and then this is the now this is the input binding. Okay, so again I use the same input file and then same number of data, okay, and then I have the 12 different bin sizes, okay, 1, 2, 4, 8, and so on, okay, up to 2048. So in the case when there's a bin size is the 2048, then there are only 2 blocks because the total number of data is 4096, okay. Yeah. So now let me run the code. Okay, now you can see it, okay. When the bin size is 1, okay, then each measurement presumably just yeah, so in this case then the error estimate, the error is just this is the mean value and this is the error, okay. So as you can see, this error is exactly the same as the one here, right, exactly here. So this is the only the one variance, okay, of the A divided by N, okay, the square root, okay, so this is the sigma over square N, okay, so this is the error, okay, and here you can see the same, okay, yeah. Now you increase the bin size and then the error changes, okay, become larger, okay, so this is the smallest and then larger, okay, and then larger, okay. And then here you can see, okay, this is the, around here is the more or less layer per 2 now, okay, you see. So 1.2, 1.4, 1.7, 1.9 here. So at this point, okay, yeah, you can be, it's still increasing, okay, but it's quite slowly, okay, okay, so here. So you can regard as say 2.34. You can see. Okay. So this is the per 2. Okay, you can see. Okay, this is really per 2 now. 2.37, 3.4, and then 2.2. Okay, so this around this is a per 2. Okay, so that means that at the bin size 128 and have 32 blocks. Okay. And then you can see the mean value is more or less the same, but not exactly the same. Okay, yeah, you can see. Yeah, the difference is negligible. Okay, because the difference, okay, is smaller than the error. Okay, estimate. Okay, so in this case, okay, you can see the plateau is here. Okay, yeah, when you change the bin size, okay, you get more or less the same error. Okay, so I will take either, you can take, say, for example, 2.3, 2.4, 2.2, 2.2. Okay, so you can see, you can have the form of root is this. Okay, you see increasing to the maximum and then you decrease. Okay, and then the maximum, you can just take the maximum. Okay, here. So this is the 2.214. Then I will take this as the error estimate. Okay, and so in this case, this 2.4 times 10 to minus 5. Okay, and compared to the measurement by the autocorrelation, oh, it's too good to be true. Now this 2.48. Okay, so this, you see, you can see, okay, the binding and the autocorrelation measurement are consistent. Okay, yeah. Okay, so it is 2.4 something. Okay. Remember, this is only an error estimate, okay? You should not worry about, these two approach get exactly the same result. No, okay. Yeah, it's an error estimate, okay? And this is a different method, error estimate, obtain the consistent estimate, consistent answer, okay, to the error. Okay, so I always use the binding, okay, method to get the to estimate the error, okay, and not only binding, but binding with the jackknife, okay. Jackknife, I don't have a chance to tell you, okay. I don't have time to tell you the details, okay. But based on the same, this jackknife sample and then binding, okay. For my data, I cannot measure the autocorrelation, okay. But the binding is always possible, no matter how many data you have measured. You can always use the binding to estimate the error, okay. And then from the pet 2 or from the when you increase, when the error increasing to the some maximum and then decrease, and then you can just take the maximum here, okay, local maximum, okay. Sometimes, okay, you can see when you decrease and then increase again, then it doesn't matter, okay, you don't have to worry about it, okay. Here is the pet 2, okay. So when you increase to a maximum, and then that's it, you take this. And then you decrease, okay, 2.4 decrease to it. Decrease it, and then you further can increase or decrease, doesn't matter. You don't worry about it, okay, because this fluctuation is due to the number of blocks is small, okay. So you cannot get an estimate, good estimate, okay, of the error, okay, by the so small number of blocks, okay. Okay, so any questions about the error in Monte Carlo simulation? Okay, with the correlated measurement, okay, statistically correlated measurement. Yeah. If you assume they are all statistically independent, and this is the naive estimate, but then if you measure it, okay, to see whether it is the has a correlation, then you find out, okay, it correlated, and then the error is large by a factor of 4 something. Okay. In the problem set, let's see. Let me go to the another window. Okay. Switch to another window. Here. Big, okay. It's too small. Okay, yeah. So there's Monte Carlo GPU accelerated Monte Carlo simulation on 2D Ising model of the lattice. Okay. So you are asked to do a simulation on the 200 by 200 lattice, okay, and then determine what's the optimal block size, okay, to perform the Monte Carlo simulation at B equals 0. And then with this optimal block size to do the simulation, okay, at different temperatures, okay. So at 6 temperatures, and they measure the energy and the energy density and the metallization density, and estimate the error respectively. So in this case, the error, okay, you have to estimate the error, okay, with the either by the measuring the autocorrelation or by binding method. So either method, okay, you can try, okay. But the first thing is that you have to output your measurement, okay, to a file, okay, with the E and M, okay, for each measurement, and then you can read the observable, okay, and then estimate the error of the mean, okay, yeah. And then with a table, and then plot the result as a function of t, okay. Yeah. So this is the one of the problem. The other problems, problem 2 is yeah. So yeah, see if you can write a simulation of 2D zinc model, okay, using 2 GPUs, okay, or for the multi GPUs, okay, yeah, yeah. And then the problem 3 is the repeated simulation. Repeat this simulation, okay, using 2 GPU rather than 1 GPU, okay, yeah. So, and then yeah, see you get a consistent result or not, yeah. So, yeah, since each problem set is only required to work out one problem, okay. Of course, you can work out all 3 problems, okay. It's up to you, okay. So, yeah. So, yeah, if you are 3, okay, then you don't have to work out 1, okay, because it's more or less the same, except you are using 1 GPU and this using the 2 GPU, okay. And then the analysis is the same, okay. So, yeah. So measure the energy, the magnetization, and the error estimate are all the same, okay. Yeah. Except the simulation result, okay, obtained by 2 GPU simulation rather than 1 GPU simulation for the problem 3 here. Okay. Okay. So we've finished the Ising model simulation of Ising model. Okay. And we go to next topic. Okay. Okay. Yeah. So I want to talk about this unified memory. Okay. So it is one of the features of the CUDA, and it could turn out to be handy. Okay. Yeah. Is but I will tell you. Okay. How it works, and then yeah, in whether it's more is more convenient, but whether it's more efficient, okay, more faster, okay, yeah, you can tell, okay, yeah. So depends on your code, okay, yeah, yeah. So let's look at the GTX 1060, okay. So this is the 2 GPU cards on the motherboard, okay. So we have different kinds of memory, okay. So in general, we have the CPU and then the system memory, okay, on the motherboard, okay. And then the device memory is on the GPU card, okay. You have a GPU 0, 1, 2, for example. Yeah, in this case, only GPU 0 and GPU 1, okay. And then device memory is inside the GPU, inside the GPU card, okay. So yeah. So in general, okay, yeah, the CPU, okay, yeah, can only copy the data to GPU, and then the GPU device memory, okay, then copy the data to the CPU, the system memory, okay, yeah. And so far, I did not tell you CPU can actually, okay, go use the memory, okay, in GPU. And the GPU can also use the system memory, okay, for the computation, okay. Yeah, I mean, all the memory, okay, GPU or CPU memory, okay, yeah, they are available to both CPU and GPU, okay. Yeah. So yeah. So unified memory is this idea, okay? Is yeah, make this system memory and the device memory unify these two memory such that all devices can use this memory space. Okay, so this is the unified memory. Okay, so yeah, so unified memory is something artificial. Okay, just there's no hardware unified memory. Okay, so only from the programmer point of view. Okay, there's a unified memory. But so in when you use unified memory, you have to remember that efficiency, okay, may not be the same, okay, as you regard it as the device memory or regard it as the system memory, okay. For GPU, okay, it always seems to be faster to use the device memory, okay, rather than regard it as a unified memory, okay. And similarly for the CPU, okay, if you declare array, okay, in the CPU rather than declare it as a unified memory, okay, rather than access it through the unified memory, then usually it's much faster. Okay, so the unified memory is only in the case when the GPU memory, okay, may not be large enough, then you want to use unified memory, and then such that, okay, some of the system memory, okay, can be used for storing the memory for your GPU calculation. But then the price you pay for it, okay, is the efficiency, okay, may not be so good, okay, because there's hidden overhead, okay, due to the data transfer from the system memory to the device memory, okay, which is the you don't know, okay, for programmer you don't know, okay, but for the hardware, okay, it actually happens, okay. So anyway, there's a unified memory, you can use, okay, in CUDA. So it's a single address space accessible from any processor in the system, okay. So this is the hardware software technology allowing application to allocate data can be read or written from code running on either CPU or GPU, okay. So no matter it's a CPU or GPU, okay, you can always use this called unified memory, okay. So as long as when you allocate a memory space, okay, as a unified memory, then this unified memory can be accessed by both CPU and GPU. Okay, so instead of manlock and CUDA manlock, okay, manlock is usually just say for the CPU, okay, in the system memory, and CUDA manlock, okay, is the allocate the space in the memory space in the GPU in the device memory, okay. But for unified memory, you always say CUDA manlock managed, okay. Then this array is in the unified memory, and it can be accessed by the CPU or GPU. Okay, so so it's a very nice, okay, feature, okay, the code, okay, you don't have to say copy back and forth, okay, but there's as I said, okay, there's some underlying overhead, okay, which we don't know, okay. So CUDA memory copy, okay, host to device or device from host. This can be saved, okay. If it's in the unified memory, then you don't have to copy it from device to host or host to device, okay. Since once it's in the unified memory, both host and device can access that, okay. So you don't have to transfer, okay. So let me go to this example, okay. This vector addition with multi GPUs, okay. So this you know, okay. This is the CUDA manual, okay. This is this is the code discussed before. Okay, but now instead of say using the CUDA, CUDA menu, okay, I just allocate the unified memory for the CPU and the GPU. These three array A, B, and C. Okay. Okay, and then A can access these three array can be accessed by both CPU and GPU. Okay. So you can see, okay, this I don't have to copy the data from host to device. Okay. And then after the summation of the additional two vector A, B, and C, result C, and then I don't have to copy the data from C to the CPU. Okay. CPU already can access, can see it. Okay. So yeah. Okay. Let me go to the code. And here. Okay. Vector addition. Unified memory. And GPU. Unified memory. Okay. So let me first look at this. CPU. Okay. Host vector HA, HB, HC, and HD. Okay. Yeah. And this is the kernel. Okay. So this is the same as before. Okay. Now, the only everything else is the same as before, you know. Okay. So let me go point out the difference here. Okay. So here, allocate the unified memory. Okay. So I allocate these three. So these three array HA, HB, and HC. Okay. Yeah. To be unified memory. Okay. So that means this HA, HB, HC. Okay. Not only for the host, but also device can also see it. Okay. Then initialize it. Okay. Okay. And then hammer and all this, you know. Okay. Yeah. And launch the kernel. Okay. So you can see, okay, I use the HA, HB, and HC, okay? So only just, so far, I only have these three array, okay? I don't have the DA, DB, and DC, okay? Yeah. And then that's it, okay? And here, HD, okay? For HD is the array, okay? And I did not indicate is as a unified memory, okay? So HD, okay, is the manlock, okay? So it's in the system memory, okay? Yeah. So and then I do the compute the reference solution, okay? Yeah. But HAHB is in the unified memory, okay? HD is not, okay? HA and HB in the system in the unified memory, okay? So I get the result and then check the result, okay, and see C and HD, okay, any difference or not, okay, yeah, and then that's it, okay. So this code is more or less the same as before for the vector addition with multi GPU. Only difference is the unified memory, okay. So yeah, and then I have the input here. Input, okay, one GPU first. Okay, G1. Okay. So one GPU and then the device number. Okay, which device? Okay, so this is assigned by the condo. Okay, and then the vector is a 2 to the power 27. Okay, so this is the size. And the block size I just choose 32. Okay, yeah. Okay. So the result is this, T1. Okay. So you can see the processing time. Okay. Yeah. GPU is speed up factor 3. Okay. Now, wait a minute. Okay, this 3 seems quite large speed up. Okay. Yeah, compared to the what we see. Okay, in the case of the using the device memory and the system memory in the host. Okay, so in previously we got HA, HB, HC, HD. Okay, in the system memory in the CPU, and then the DA, DB, DC. Okay, in the device memory. Okay, so let's see. Okay, what are the results in the okay here? Yeah, you can see. Okay, this is G1. Okay, actually, so this is exactly the same length of the array. Okay, so the vectors. Okay, is 2 to the power 27. Okay, A and B are two random vector. Okay, and everything is the same. Okay, all you see input all the same. Yeah. And then output here, G1. Okay, now you can see the difference. Okay, so output for the so the total time for a GPU is 379 millisecond. Okay, let me see what we have here for the unified memory. Okay, so unified memory is 230 milliseconds for the GPU. Okay, gigaflop is 1.88. Okay, and for the you see for a GPU time here, if I use the device memory, 193 milliseconds. So this is 213 seconds. So this using unified memory is a little bit slower. Okay, slower. Okay. Yeah, but since there's no you see there's no I/O time. Okay, so the GPU gigaflops 12.5 gigaflops. Okay, because data input time, processing time for the GPU. There's no. Let's see, data input time for a GPU. 100, so 193. Let's see. So the total is 193 milliseconds. Okay, and this 213 milliseconds. Okay. So the processing time, okay, yeah. Is the processing time here is the 32. So here I should have this is the data output time 100. So total time for sorry. Total time for GPU. This one is the total time for a GPU is the 379. So 380 millisecond. Okay. But for the unified memory, okay, you can see this is the processing time for a GPU, okay, because I don't have to count the I/O time, okay, input time, output time, okay. So this is a 213 millisecond, okay, processing time for the GPU, okay. So the processing time for the GPU in the case of the device memory 379 milliseconds. So you can see, okay, this unified memory actually has an advantage. Okay, yeah, it's faster, right? Yeah, you don't have the explicit, okay, I/O. Okay, I don't have to transfer data from the CPU to GPU, and then transfer data back from the GPU to CPU. Okay, so this is the counting the time. Okay, only the kernel. Okay, only the kernel. Okay, because I'm using HA, HB, and HC. Okay, in the kernel. Okay, and so the time is much faster than if I use the device memory. Okay, yeah, use unified memory is faster. Okay, and let's look at the CPU time. CPU time is 600 millisecond. Okay, but here, for example, CPU in the case when I HA, HB, and unified memory. Okay, so this is the slower. Okay, so this is 683 rather than 607. Okay. So you can see, okay, for the CPU, if the HA and HB, okay, is declared as the unified memory, then the CPU has, I mean, yeah, will be not so effective, okay, to getting this the memory, okay, yeah. So in order to get a more fair comparison, okay, let me go to the unified memory case, okay, and GPU and unified memory, okay. I prepare another version of the code, and then, yeah, I have the HAA and HBB, okay, here. So, so these three are not the unified memory. Only HA, HB, and HC are unified memory, okay? Okay. Then you can see, okay, the CPU operation are all using the system memory, okay? Not these three array are not unified memory at all, okay? HG and HAA and HBB, okay? So you can see, okay, here, after when I initialize HA, HB, and I copy this to HAA, HBB, okay. So HAA, HBB allocate the host memory accessible to CPU only, okay, only the system memory, okay, not unified memory, okay. So see how whether this has a difference, okay. So G1A, okay. So you can see the processing time for the CPU is 524. Okay, 524, and then before it was here 683. Okay, so you can see, okay, yeah, when this is a unified memory, so the CPU, okay, is not so efficient for a CPU. Okay, but it's very good, okay, optimized for the GPU. Okay, so for a GPU, yeah, if the I/O time, okay, really play a large fraction of your in your code. Yeah, any questions? Any questions? I hear you. Someone say something. Huh? No? So you can see this is the GPU is the 213, okay? Yeah, compared to the using the device memory, okay? Using device memory is let's see here, this one is adding together is 380 milliseconds, okay? So so you can so this break down it, then you can see clearly, okay? Yeah, the advantage of the using the unified memory, okay? So the unified memory is good for the for a GPU, okay? Yeah, but for a CPU, okay, yeah, there is an overhead, okay, okay, yeah. In this case, okay, this 607 millisecond for a CPU is still not consistent with the one with the 524 here, okay? 524, okay, yeah, is the yeah, yeah, all HA, HB, and yeah, HDD, okay, HD, okay, they are all CPU manual, okay, yeah, so they are in the system memory, okay, so there's still difference, okay, yeah. Yeah, but for CPU here, of course, the same, okay, 215, and this is the two, yeah, here, okay, 213, okay, so those is consistent, okay, yeah, 524 here, maybe the CPU here is the different CPU, okay, because I have the two nodes, okay, one is the TLQCD 80, the other is the TLQCD 218, okay, so this two GPU has a different, they're not the same, okay, so maybe this is the difference, why this 524, the other is the 600 something. Yeah, this one is the 607. Okay, yeah 607 and 683 are the same GPU. Okay, so this 6383. Okay, because the unified memory, the CPU takes more time. Okay, yeah, CPU computation. Okay, take more time. So now let me go to the two GPU. Okay, two GPU. So you can see the for example, the two GPU actually is the half of it, half of the one GPU. Okay, so this is the one almost factor of divided by two. Okay, almost. Okay, yeah. And this 682, of course, is consistent with the previous one GPU. Okay, yeah. So the speed up here is a 6.0 compared to 3 point something. Okay, yeah, compared to this one. Yeah, 3.19. Okay, yeah. Okay, so this is the use the unified memory, and for one GPU, and this is for two GPU. Okay, yeah. Okay. And since the system has some problem, I cannot run the code. Okay, submit the code to the condo, and then so this is the old results. Okay, so I just copy this to the, so you can access the code. Okay. Okay. Any questions? Yeah. So you can see the advantage of using the unified memory. Okay. Or especially for the GPU code. Okay. But depends on your problem. Okay. Yeah. If your problem is not so the I/O. Okay. Does not matter so much. Okay. Say for example in the Laplace. Okay. So only it won't affect too much. Okay. If you decay as a unified memory. Okay. Yeah. But you can try. Okay. See if you can decay as a unified memory. Then you will have a speed up a lot. Okay. Yeah. Okay. Next lecture, I'm going to talk about the fast Fourier transform. Okay. So the next two lectures, okay, might be on the CUDA library. Okay. The FFT. FFT is one of the important library in the CUDA. And then other libraries are important for the science and engineering is the BLAS, basic linear algebra, subroutine, and also the magma, okay, the eigen values, okay, and the solving the linear equations, okay, the LinPack, the GPU version of the LinPack, and actually the GPU version, the magma is the GPU version of the LabPack, okay, LAPAC, okay, LPACK, LabPack, okay, yeah. So I would like to talk about these libraries, okay, these three libraries, okay, yeah. But next time I'm going to talk about the fast Fourier transform, but then and then the next week after the next week, okay, so that's the end of the May, okay, so there's the May 30, okay. But I look at the calendar, okay, the May 30 is holiday, okay, the makeup holiday for the Dragon Boat Festival, okay. So do you want to have a lecture on May 30? Yeah. Yeah, if we have a lecture on May 30, anyone has difficulty or not? Anyway, you let me know, okay, yeah, whether you want the lecture on May 30 or not, okay? Yeah, if not, then I see you, I can cover, yeah, some, next week, okay, I must be able to cover the fast Fourier transform, okay? And there's a problem set 9